All right, we've talked about arithmetic sequences and series. Now we need to talk about something called geometric. And I'm going to give you some examples just so you can get a sense of what's going on here, okay? Here are 3 examples. Again, you don't have to write all of it down, but maybe parts of them down. And try to figure out what the pattern is. And just write down what the pattern is. Don't tell me yet. Just write down what the pattern is, what you think the pattern is. And then we'll talk about why these end up being geometric sequences. So, all right, Braden, you said you wanted to tell us what the pattern was for the first one. So what is the pattern?
Oh, it's times 3.
Times 3, okay. All right, somebody want to volunteer for the second one? Eli, what you got? Times 4. All right, how about the last one? Anyone want to take a shot at that one? Times 1/4. So keep in mind, like what we did when we did arithmetic, of course it's dividing by 4, right? It's dividing by 4. But we think about it the same way we thought about arithmetic. Arithmetic was always addition, even adding negative numbers. For geometric sequences, it's always multiplying. Now, when you multiply, you could multiply by a fraction. Some of the common, what was the common difference for arithmetic, we call something different for this. Some of those are going to be a little trickier to find. But that is what a geometric sequence is. It basically is just, and I said something like this for the arithmetic, but it's when a sequence goes up or down by the same amount when multiplying. So just like when we did arithmetic, we always said addition. For geometric sequences, we always say multiplication. Even if it is a fraction in reality, in your mind, you want to think about it as division. We're always going to talk about multiplication because we have to have that same thing that's like the common difference, but we're going to call it something different for geometric, and we'll get to that in a second. There, it's fixed now. A geometric sequence. Yeah, I copy and pasted it from the other one where it said an arithmetic sequence. All right, let's get to the part where we start breaking down formulas and things like that and discussing where they come from. So here's the start of the box. We're going to fill the rest of it in. Of course, any geometric sequence, the notation is the same as what it was for arithmetic. The braces mean the entire sequence. Here's the first term. To get the second term, you take the first term times r. So r is what we're going to call that common quote-unquote difference, the multiplier. Here we're going to call it a common ratio. And will that be here? I don't remember. Okay. So this is what's called the common ratio r. So like arithmetic sequences where we said the common difference or we added the same thing every time, in geometric sequences we multiply by the same thing every time, and that r is called the common ratio. And there's some similarities here, okay? To get from the first term to the second term, we multiply the first term by r, and that's where the second term comes from. Then you take this, multiply it by r, and you get the third term. So that's why it's r squared. Then you take and multiply this by r to get the fourth term. So that's why it's r to the third. And it goes on and on forever. So that n minus 1 thing is going to come back into play here, except instead of being multiplied by the common difference like it was, we're going to raise it to a power, okay? The other thing to keep in mind is that when you're trying to find the common ratio, I will tell you that some of the problems in your homework today, and actually some of the examples we're going to go through, it's not easy to tell. Like those first 3 examples that we had, it was pretty easy to figure out what the numbers were going to be. There are going to be ones where they aren't as easy to find out. And so in order to figure out what that common ratio is, you just take a term and divide it by the term before. Or take this term and divide it by the term before. It's all going to depend on what they provide you in your homework. But so this is how you find the common ratio. So this is the term we're at. This is the next term. By now we should be good at this, understanding what n plus 1 notation n is. So this is the term that comes after this term. It could have just as easily been written like this. A sub n over the term that came before it. Means the same thing. So long as you take 2 terms and you divide them with the higher numbered term on top, then you will get the common ratio if it is a geometric sequence. All right, so now let's get into the actual formula that you're going to be using. And here's that formula. Okay. So the nth term of any sequence, and like I said, here's where that n minus 1 comes in. You take the first term times the common ratio raised to the power that is 1 less than the term that we're looking for. So for example, this is the 1, 2, 3, this is the fourth term. And so I raise r to the third, 1 less than 4. Because my first term is r to the 0 power, which is 1. You don't have to multiply by anything. But to get from the first term to the second term, now it's r to the first. Third term, r to the second. Fourth term, r to the third. Fifth term, r to the fourth. So the power that you raise r to is always 1 less than the term you're looking for. Now, I will tell you that in a lot of these problems, these are going to be calculator heavy because you're going to have some large numbers or really, really small numbers in case the common ratio is a fraction. And you raise those to large powers, you're going to get really large numbers if r is an integer. You'll get really small numbers if r is a fraction. So that's going to come into play today. That is a formula that I've underlined that you're going to have to know for your test next week. This, in either form, you're going to want to just kind of understand that. I don't know that you necessarily need to memorize a formula for this, for the common ratio, but you're going to have to find the common ratio at times, and at times it's going to be harder to do. So using that's going to be important. Are there any questions so far?
Yeah, the test multiple choice.
Yes. All right. The last part that I want to talk about on this page is the recursive formula. So the recursive formula is going to be in play again. And remember what that means. It means I need to find the next term, I need the previous term. So for example, in order to find the sixth term, I need the fourth term. And so you just keep using the term before to come up with the next one. And that's what this is explaining, okay? So just like the recursive formula from arithmetic, there's only two things that ever change. All right, what I've highlighted in blue there are the things that will change. This a sub n will always be there. Equals a sub n minus 1, that will always be there. For n greater than or equal to 2, that will always be there. The only parts that change are whatever the first term is and whatever the common ratio is. So it's very similar to arithmetic sequences written recursively in that way. Obviously, since we're multiplying, it's a little bit different. Again, the restriction is there has to be at least two terms. N greater than or equal to 2 means there are two or more terms. And most of the times, there'll be way more than that. Otherwise, if it was just one term, it can't be a sequence if you just write one number down.
What is R?
R is the common ratio. R is what you multiply by every time. Okay. So that's the key thing here. I'm just getting a little bit to it. Again, you can recognize by dividing any term by the first one, by the one before it. Okay. And this is just explaining whether or not you need to write this down. That's up to you. It's just explaining this. It's just explaining why that all works out the way it does. Again, write it down if you need to. Okay. So we're going to go through some examples, and then we'll talk about series and adding them up. And there's a long proof in this about where the series formula comes from, and you won't have to write that down, but you can just pay attention to where it comes from, and I'll go through that fairly quickly. But let's do some examples of sequences first, okay? So here's the first example we want to go through, okay? So this is example 1. We have two examples here. Determine whether or not the sequence is geometric, and then if it is, write the common ratio. If it's not, then write that it's not, okay? So go ahead and do those, and then we'll talk about it. Is the first one geometric? Do you multiply by the same thing every time?
Yes.
What do you multiply by? Multiply by 1/3. Okay, if you weren't sure if it was the same, what you would have to do is do some division, okay? And you'd want to do a couple of them, right? Just to make sure that they always equal 1/3. And so in this case, they do all equal 1/3. So this one is definitely yes. And you wouldn't necessarily have to write it all out like this, but you could really just say yes, common ratios 1/3. That would be enough for me. Okay. I know there's a lot of writing there. I just copied that from the book, but saying what the common ratio is, and then also saying that yes, it is geometric, then you're good. Okay. How many had that? All right, good. How about B? Yes, no?
No.
Why not?
Oh, the last one.
Yeah, so we have an issue right here. It's 4, then it's 4, then it's 5. Okay, so the trick is you got to check enough of them. And we run into an issue right here. So the next one, and again, this is with it all written out. I don't necessarily think you have to write it all out, especially for problems like this where it's fairly simple. So this is definitely a no, and because of that. And you'd want to indicate it, express it somehow, write it out a little bit. I'm not going to get too hung up about that. But if you're asked to find out why, then you should probably explain it. All right, let's move on to another example. Okay. First 5 terms. So here they've only given us one term. So in this case, we have a sub 1, which is 5. I need to find a sub 2, a sub 3, a sub 4, and a sub 5. So please do that. You've got a couple options of how to do this, right? I don't care which way you do it. I want you to do it the way that makes the most sense to you. So there's a couple ways that we can come up with all these numbers. Whatever way seems easiest and makes more sense to you is the way you should do it. So in order to get from the first term to the second term, what should I do?
Multiply by negative 2.
Yeah, multiply by negative 2. So what is the second term?
Negative 10.
Okay, and so you could just keep doing that, multiplying by negative 2. And then what am I going to get for the next one? 20. Then what? Negative 40. 80. Okay, you can do it that way. You can use the formula if you want. Again, either way, whatever gets you to the answer is fine. And here is showing you both. Okay, so this is what we just did, which we did it recursively. That is a recursive formula. Okay, you take the answer you just got, multiply it by 2 to get the next answer. So you always need the previous number to get the next one. Now, if it was asking for a specific term, then it would make more sense to use the formulas. But here the formula is the first term times r to the n minus 1. So since r is 2, this is negative 2 to the first. N is 3 to the second, 4 to the third, etc. It gets you the same thing. In the end, you have both options. I don't care which one you use. Whichever way makes the most sense for you, great. Okay? All right, so now let's get into one where we're looking for a specific term. Now, here's where knowing the formula is going to be more helpful usually, because trying to find all the numbers and doing all the multiplications, and if the numbers get too big, etc., when you don't need all the other numbers. When you have a formula, then finding a specific term really isn't that difficult. The trick here is we're looking for the fifth term. We're looking for the fifth term. Now, Could I take the first term and find the second term, third term, fourth term, fifth term, and do it that way? Of course. But you know as well as I do that come test time, it's going to say find the ninth term or something like that, where it's just not going to be it's going to be too cumbersome to find them all instead of just using the formula. All right, so let's start with the formula. The formula for a any term in the geometric sequence is a sub n equals the first term times r to the n minus 1. And I put it in parentheses because depending on what kind of calculator you have, that will dictate whether or not you need the parentheses. Some of you have an older calculator and you need to put the parentheses in the power. Some of you have a newer calculator and you can just keep typing in the exponent and it's fine. All right, so what we're looking for here is we are looking for the fifth term. So everything in blue is unique to this problem. What is the first term here? 15. Do we know r yet? I mean, we got to find it, and it's not nice, right? It's not like I'm multiplying 15 by something nice to come up with that. So let's hold off on r for now. Okay. The n minus 1, we know that's going to be the fourth power. So we really just need r and we're done, basically. Okay. And so like I stated earlier, finding r is going to be tricky for some of these problems. Just take the higher numbered term and divide it by the term right before. So in this case, they've only given us a sub 2 and a sub 1. So you take the higher numbered term, not necessarily the higher term, the higher numbered term on top, and then divide it by the one right before it. So in this case, what my common ratio is negative 9 over 15, which reduces down to negative 3/5. That is the common ratio. So this is, like I said, this is where you're going to definitely want to calculate. I don't think you're going to want to do negative 3/5 to the fourth power in your head. I guess you could, but I mean, I wouldn't. So this is a to the fifth equals 15 times negative 3/5, and I put that all in parentheses to the fourth power. Now I would enter this all in the calculator just like that. But this is the work you show. You fill the formula out, and then we're just in good shape to figure this out, okay? So go ahead and type that in and let's see what you get. Negative 36 even?
I got 1.944. What's wrong?
All right, so we got all kinds of different answers. Well, I'll do it without a calculator and we'll see.
Oh,
all right.
Big flex.
Yeah, that's right. This is 81 over 625. 3 to the fourth is 81. 5 to the fourth is 625. So now, I can cancel some stuff. What goes into 15 and 625? 5. So that would be a 3, and this would be a 125. Okay. So then I've simplified everything I can. 81 only has 3's in it, and this doesn't have a 3 in it, and 3's up top. So my final answer, if I multiply the top, is 243 over 125. Now, I heard some of you say that, so good job.
Isn't that 1.944?
I have no idea.
It's gotta be.
Yeah, it's probably pretty close to 2 because
So
1
could I
point.
put a
So how come?
decimal?
No, please do not put a
How
decimal.
do I get my calculator to give
We can.
math?
Now, so in reality, what I want here is fractions. Now, I guess if you changed this, let's say you changed this to a decimal, and when you did the problem, you considered r negative 0.6. I guess if you would have done that, then you could have plugged it in. But did your decimal repeat? Did it go on forever, or did it end?
No, it's just 1.944.
And that was it.
Yeah.
Yeah, so that would be okay, I guess. So if you wanted to, if you did use your common ratio as a decimal, this is also equal to negative, I'm sorry, not negative, 1.944. So if it ends, that's okay. Now, when you go to, we're checking answers and stuff, I will tell you that most of the time the answers are going to be fractions when possible, but we can flow in between. All right. Let's see. Here's another one. Finding a specific term, but this one's going to be a little trickier. All right.
Which example?
This is example 4.
Just did that.
Oh, no, we just did that one. My bad. No, that's just all the work that I skipped over. All right. Yeah. Next. Let's talk about series. Make sure that was the end of that one. Okay. So let's talk about partial sums. All right. Now, what I'm about to show you, you do not need to write down. This is the proof of where the formula comes from. Okay. I'm going to go through it fairly quickly, just like we did when we did the nth partial sum for arithmetic. I'm going to go through where this formula comes from. You don't need to know this. You don't need to write this down. It's just FYI, so you see where this formula came from. All right. So if we have our sequence, or nth partial sum, and it's a sub 1 plus a sub 1 times r, and all the way to the end, and the last term is going to be a sub 1 to the r times r to the n minus 1. All right. Now, if we subtract it, now notice here, this s sub n gets multiplied by r, and you'll see why in a second. So if we subtract those two, so essentially I take this, multiply them all by r, and then I subtract them. What you're going to see is that there's an extra r. So this is what it looks like all written out. So this is s sub n minus r s sub n. This one here is a sub 1 minus a sub 1 minus r. Again, you don't need to know this. I'm just showing you where this formula comes from. And then what we can do is we can do a little factoring. All right. And then there's some canceling that's going to go on. So notice here in the middle that I have a minus a sub 1 r and a plus a sub 1 r. And then a minus a sub 1 r squared and a plus a sub. So basically everything in the middle is going to cancel, except I'm going to have this leftover term and this leftover term. All right, so this is a sub 1. This is what's in blue. And this is minus. This is the only thing that doesn't cancel out. Now here I'm going to factor out this s sub n. Okay. And I can factor out an a sub 1. And so in order to find the sum, all I've got to do is divide both sides by 1 minus r. And that is the formula. Okay. So, yeah, that's okay. Like I said, you don't need to know it. I was just showing you what it all is. So this formula is for an nth partial sum of a geometric sequence.
That we need
Okay.
to know.
That you need to know that I know. Yes. That's how you find the sum, because in order with the geometric sequence, you're going to still have to, the nth partial sum means you got to add up all the terms. Well, this is the proof as to why you don't actually have to add up all the terms. If you use this formula, you take the first term times 1 minus the r to the nth power divided by 1 minus r. So this is really what we call a finite geometric series. That's what an nth partial sum is, finite, and we're going to talk more about that. And then we're going to talk about infinite geometric series as well. Yeah, so this is the second formula, well, really the third formula, fourth formula, technically. We have the recursive formula, you have the how to find the common ratio, how to find a specific term, and then you have the sum. Okay, so that is the next formula you're going to need to memorize. We'll work through a couple examples, and then we'll get into some really abstract concepts, because I think those are important to understanding what we're doing here. Okay, and then we'll be done.
It's gonna be a lot of adding in that test.
Yeah, so if you don't memorize the formula, yes, you're gonna have to add all that up, which would be a real pain. So those of you who did that on the quiz yesterday, you know, because you didn't study the formulas, you know, it does work. It
12
does
to
work.
72 was crazy.
Yeah, and
Long equations.
here's the other thing: your test is on a block day, so you have extra time to do all that crazy adding. Or, I mean, if you fail to remember the formula, and we'll review it right before the test anyway. But anyway, all right, let's do an example. Okay, so we're gonna. This is a finite geometric series, which is the same thing as a finite. Is the nth partial sum of a geometric sequence. Those are the same thing. Okay, so here we're finding the sum. We have 6 terms. Okay. Now, if you know the first term, and you know what r is, and you know how many terms there are, then you'll have everything. All right. The first thing we need to do is make sure this is a geometric or arithmetic sequence so we know which formula to use. So you got to find the first 3 terms. Okay, so let's do that. So the first term. Okay, so I'm going to plug 1 in for I, which this is 4 times 1/2 to the 0, which, what is all that? What is 1/2 to the 0? 1. So that's 4 times 1. Okay? All right, let's find the second term. 4 times 1/2 to the 2 minus 1, which is 4 to the 1/2 to the first, so that is what? 2. So what should the next term be if it's geometric?
Should be 1.
It should be 1. Multiplying by 1/2, dividing by 2, same thing. Okay? So this is 4 times 1/2 to the 3 minus 1, which is 4 times 1/2 to the second. What is 1/2 to the second? 1/4. So we're good. So R is, what's R? 1/2. Not a coincidence. Okay, that 1/2 in the formula, the original sigma notation, is also the common ratio. All right, so now that we've established that, we can go to our formula. So our formula is S sub n equals the first term times 1 minus r to the n all over 1 minus r. And so it's just a matter of plugging into that formula and we're done, basically. Do we know what n is? What is n?
I know n is 6.
It is 6. Since this is 1, the top number is going to be the number of terms. There are 6 terms. So n is 6. So from here, it's just a matter of plugging in. What is the first term?
4.
4. 1 minus r, we decided, was 1/2. We got to raise that to the 6th power because that's n. And this is 1 minus 1/2 because that's what r is. All right, figure out what that is. Go. If you attempt to plug all of this in the calculator at once, be very, very careful. 1, if you can figure out how to create a fraction on your calculator, that will make this easier. If you have a calculator that's too old, you may need an extra set of parentheses. For example, you may need to put an entire double set of parentheses around that, and then you have to put your division sign. And then you'll have to put another set of parentheses around this. Okay? That's one option. The other thing you could do is do a part at a time. Like just do the inside first. Then multiply by 4 and figure that out, and then do the bottom, and then combine them together, okay? At this point, you should have enough command of your calculator to know which way is going to work best for you, but ultimately, the work that I need to see is this, okay? And how you put it in there is kind of up to you.
Does that work?
Let's see.
You didn't do 1 minus 1/2 on the bottom.
which he did 1 minus 1/2. Yeah, that should work. That should do it. So however you come up with it, that's up to you. I don't care. But just make sure you do it right. Okay? Ultimately, that's what really matters. Okay. Now you should have gotten this. The final answer should be 63/8. Okay. Again, I do not expect you to do this out by hand. You can, and you could write that down. But ultimately, since this problem has fractions in it to start, the formula is fractions. So I really want you to have your answer in fractions. Okay? So if you're getting decimals, convert it over to a fraction. You don't need to change it to, I know I see a mixed number over there. I don't need mixed numbers. You can leave them improper. That's fine. But you should have got 63/8. These fractions can get kind of ugly, especially when your common ratio is a fraction. So you just have to be really careful when you enter everything in the formula. Make sure you enter it in properly. Then when you enter it in your calculator. If you don't trust yourself to enter it in the calculator correctly, then do one part at a time like this, okay? And then combine that times 4 divided by 1/2. We know that, hopefully by now you know that dividing by 1/2 is the same thing as multiplying by 2. All right, next, moving on. Let's do another one.
How many examples?
Okay. We have another thing to go over after we go through this example. Okay, evaluating a finite geometric series. Okay, what is the problem here? What's the issue? Why is this different than the last one?
It's dividing.
No, it's not. Times 1.5.
I can't see that.
Nope.
Looks like it's times 2.
Yeah, it's definitely times 2. But what else? What don't we know?
Oh, we don't know all the other.
How many?
We're gonna have to plug in
How-
like
How many
520
there are?
We don't know how many there are.
for this sequence.
We don't know what n is. Okay, we can find r. We have the first term. We can find r easy enough. But we don't know how many terms there are. So we don't know n. Okay, so could you multiply and find all the terms in between and then add them up like a crazy person? Yes, you could do that. That will work. That seems awful to me though. All right, so what's better is let's figure out how many terms there are, and then we'll be able to use the formula. So keep in mind of our formula. The nth term is the first term times r to the n minus 1. Well, in this case, the n that we're trying to find, what's the common ratio?
2.
2. All right. 2 to the n minus 1. So if I could just solve for n minus 1, this problem wouldn't be so bad. Well, here's the thing. Yes, could you use logarithms to do this? You could. Because whenever, that's what logarithms are for. Logarithms are for finding when a variable is in a power. It's how you get those out of there. But there's another way, okay? There's another way to solve these, and that was getting a common base. This is stuff we did in Algebra 2. So the first thing you have to do in a problem like this is you have to get the term with the power by itself, which means I have to get rid of this 5. So what I'm going to do first is divide both sides by 5. And what this does for me is it isolates the term with the power. All right, so now we got to figure out what 5,120 divided by 5 is. 1,024. Okay, now we've got to figure out how to rewrite this as 2 to some power if it comes out even. Well, here's the thing that's nice today and why we don't actually need to use logarithms ever in this is because when we're solving for n, n represents the number of terms. N has to be a whole number. So you will always be able to change the base. Could you take the log of both sides and find n minus 1? Sure. All right? But because what n actually equals is the number of terms, and therefore is a whole number, you will always be able to change the base. So the trick here is figuring out, all right, 2 to what power? What is the power? 2 to the 10th power is 1,024. Okay, so here's what this means. Okay, in order for these two things to be equal, 10 must equal n minus 1. So if n minus 1 equals 10, what does n equal? 11. There are 11 terms. So when you get to a problem like this, where you don't know how many terms there are, you're going to have to do some calculations. Now, once we've done that, now we can actually use our sum formula. So again, nth partial sum, a sub 1 times 1 minus r to the n all over 1 minus r. So the first term is 5. 1 minus r to the, oh wait, we know what r is. R is 2 to the 11th all over 1 minus 2. So go ahead, plug that all in your calculator, see what you... All right, so this should be 10,235. So yeah, if you had to add all those terms up, that would take you a long time, and that would be really inefficient, okay? So this, with us doing the work and showing all the steps, here from the book with all the steps. Again, finding it this exact same way, except we just did it together. Okay. All right. The last thing that we need to talk about. Okay. The last thing that we need to talk about. So we've talked about finite geometric series, right? Which is just the nth partial sum of a geometric sequence. So we're adding up a very specific number of terms. There is the case where you can find the value of an infinite series, okay? Meaning you're going to add numbers up forever. And believe it or not, I mean, in our minds right away when we think about this, we think, all right, if I take numbers and add them up forever, it's going to infinity. It's never going to stop. It's always just going to get bigger and bigger and bigger, or smaller and smaller and smaller if the numbers are negative. Except there's an exception.
What?
Okay? When you take a number, a fraction, to a really high power, that fraction gets smaller and smaller and smaller. Which means when you take that number and multiply it by a number, it will also get smaller. To the point where you basically are adding 0, and so you get an answer. Okay? What we want to see is when those conditions exist. And so that's what this is all about. All right? When the R value, the common ratio, when the absolute value of R is less than 1, here's what that means, okay? That means that R is between -1 and 1, meaning it's just a regular fraction, right? Not improper, not a mixed number, a regular fraction. When R is a regular fraction, there actually is an answer. Because when you take a fraction to a really, really high power, that number gets closer and closer and closer to 0. And those of you, when you get into calculus, you're going to talk about something called limits, and that's what this is all about. The limit is as n approaches infinity of a fraction to the nth power is 0. Okay. And so what you notice here about our formula is it's really the same, except the 1 minus r to the n drops out. Okay. And that's,
Yeah, I'm completely lost.
I understand. Okay. If the R value is bigger than 1 or less than -1, the sum does not exist. So we'll say that. There's either an actual sum or the sum does not exist. And so we'll go through an example where I can kind of prove that to you. And if it does exist, if these conditions are met, you use this formula. And I'm going to show you this. I'm going to show you why it goes away. Okay. So here's the regular formula. This is the regular formula. If R is a fraction and you raise it to a really big number, this is what we say approaches 0. Well, 1 minus 0 is just 1. That's why this whole thing drops out. Right? That part of the formula drops out because since n, we're saying it's an infinite series. N goes to infinity. It goes on and on forever and ever and ever. Well, if you take a fraction, you could play with this on your calculator. Take 1/4, for example. Take 1/4 to the 100th power. And you'll see that number gets really close to 0. Take, negative 1/8 to the 100th power. That number will also get very close to 0. And so as n grows and grows and grows, this number gets closer and closer and closer to 0, where eventually we just say it does equal 0, and that's why it drops out. Okay? So let's talk about using this formula and how to decide whether or not there is a sum. Okay? We're going to look at 2 examples. All right? So notice the wording here. It says find the sum if possible. Well, to determine if it's possible, yes, there is. This is what I've just been talking about. There can be. All right. Now, the key thing here is finding out what R is. Once we know what R is, then we can decide if there's a sum or there isn't a sum. And if there's a sum, we have to figure out what it is. All right. Now we could go through all the motions for A and figure out if it was a geometric sequence or not. But one of the things that we've learned now is, what is the common ratio going to be for A? -1/3. Okay, notice the top limit is infinity for this one, and this one has the 3 dots, meaning it goes on and on forever. So what I can tell you with certainty is R for A is -1/3. Okay? Is that in between -1 and 1?
Yes.
Yes, it is. Okay? So, what this means, and this I understand the question. That means as n gets closer, as I gets closer and closer to infinity, and this number gets huge. If you I'm telling you, plug it in your calculator. Plug -1/3 in to the 100th power and see what kind of little decimal you get. It's going to be -0.0000, a bunch of zeros. And then as you go to 1,000 and 10,000, then eventually your calculator times out. It's like, it'll say overflow error, I can't do this. What this is saying is when you take a really small number and you raise it to a really big power, this whole part goes to 0, which is why, in this case, there is a sum. And it's just A sub 1 over 1 minus R.
That's the sum?
That is the sum. Okay.
That right there.
Well, I got to actually figure it out. What is the first term going to be? So we got to figure out what the first term is going to be.
5.
It's just going to be 5, because if I plug 1 in here, this is 0, which means all of this is 1. So the first term is 5. Okay, so this is 1 minus -1/3, which is the same as 4/3, which is the same as 5 times 3/4, which is 15/4. That is the sum. It actually has a sum. And again, if you don't believe me, and you don't believe the book, I'm telling you, just try plugging in some really big numbers for the power and see what happens to this. Okay? Just see what happens to this. Which means, as you get to the end of all the numbers, you basically just start adding 0. And obviously when you just start adding 0, you're not increasing or decreasing the sum anymore. Okay? All right, let's talk about B. We need to find R. To me, it's easy to ignore the first one. What's R here? How do I get from here to here? What do I multiply 8/3 by to get 32/9?
Negative 1/3.
4/3. How about, does 4 times 32 give me 128?
Yeah.
Yep. Now let's just check the first one just to be sure. Okay. 4 times 2, 1 times 3. Okay, R is 4/3. Is that in between -1 and 1? No, it's bigger than 1. It's 1 1/3. It's bigger than 1, which means this sum will keep growing. Because if I raise 4/3 to really big powers, that number just keeps getting bigger and bigger and bigger and bigger. So what we say in a case like this,
Sum does not exist.
sum, oops. And in higher level math, you'll say sum is infinity. But we don't say that. Okay?
Can I say it?
Those are your two options. Okay? Those are your two options. So it does that because if I take a number bigger than 1 and I raise it to a really, really large power, that number will continue to grow.
Right.
And so when you take a number that keeps growing and you add another number to it that is bigger than the number before, and it just keeps getting bigger and bigger and bigger and bigger, it doesn't end. So it ends up being infinity. But for the purposes here, we're just say the sum does not exist, because once you get to the 1/1,000,000th term and you add the 1/1,000,000th and 1 term, now that sum just got bigger and is different. You get to the 1/1,000,000th and second term, now that sum got bigger and is different again. But what happens here on the other end, when it's between -1 and 1, what you add gets smaller and smaller and smaller, so eventually you're adding 0. That's the difference. Okay? And again, if that concept is difficult for you to understand, I'm begging you to plug in high numbers for these powers, and you'll see that this number will get closer and closer to 0. At the same time, if you plug in a high power 4/3 to the 100th power, and then 4/3 to the 101st or 102nd, you'll see that number keeps growing and growing and growing, and it doesn't approach 0 anymore.